Today, I'll be talking about the overall concept of the Instrumented Indentation Test, or IIT, including the background for introducing IIT, its evaluation method, how to apply it to different cases, and the role that Frontics is currently playing in IIT development and implementation. Please do not hesitate to stop me if you have any questions. As we all know, in April 2010, there was an oil spill in the Gulf of Mexico. The accident was caused by a fire and a boring pipe broken by excessive load and corrosion. A few years before, in February 2007, there was also gas leakage at the LNG terminals in Incheon, Korea. That accident resulted from cracking thanks to thermal shock when a welding joint was exposed to low temperatures. These accidents are unfortunately representative of large and small incidents that continue with some frequency at industrial sites. Such accidents cause a huge loss in economic cost and unduly threaten the lives of people. To avoid further damage, it's very important to identify the potential risks of structures or facilities in operation, as well as the cause of damages that already exist. So far, periodic surveillance is used to diagnose these failures, but given the extent of these accidents, we need a more scientific and systemic manner for measuring, predicting, and developing the maintenance plan to reduce this cycle of loss. There are currently two alternate methods used for conducting safety evaluations. The more popular one checks when cracking occurs and estimates when failure will occur, but this method can hardly be applied for predicting remaining service life. On the contrary, a newer developing method that evaluates product quality enables monitoring from an early stage of a product's manufacture. More particularly, evaluation of mechanical properties enables quality assurance checks of the material's behavior as well as its reliability and safety. More research regarding this second method is not only necessary for academic purposes, but for FAD used at these industrial sites. Knowing the tensile properties of manufacturing materials is a critical step in order to proceed with a thorough evaluation of the tested products. IIT is this new technology. It is useful because it doesn't require preparing separate samples and allows fingerprinting materials by using non-destructive evaluation methods to obtain a variety of different results for even the most minute details. To be clear, IIT is not intended to replace the conventional tensile test. Rather, it is applied at sites where the conventional test can't be reliably applied or to a small object, as was specified in the ISO TR 29381. In other words, IIT enables us to obtain crucial information locally, while the tensile test provides us with the mean overall value of the sample. IIT is also useful in the laboratory and the field because it gathers information from the surface treatments alone without an invasive, separate process that is typically required now. Essentially, IIT differs because it analyzes the indentation load-depth curve instead of requiring direct measurement of a contact area after unloading. By analyzing this curve, various mechanical properties such as the true stress-strain curve, residual stress, hardness, and Young's modulus can be obtained. In addition, IIT is practical because it can be portable, so in situ, on-set testing is possible with relatively little sample preparation. It can also be applied to small samples that would normally be difficult to test, or localized sections of materials where properties are changed by parts. How exactly is IIT implemented to evaluate tensile properties and residual stress? We subdivided the algorithm for strength evaluation into 4 steps. Contact depth calibration happens at step 0, taking into account pileup and sink-in effects. True stress and true strain values are determined at step 1. Step 2 fits these values into the constitutive equation. Finally, tensile properties yield strength and tensile strength are determined. The most important things occur at step 0, which determines the contact area, and step 1's definition of true strain stress values. The whole process starts by obtaining the load depth curve. The test does not simply look at the imposed load on a material's part once, but actually measures the load at each stage by determining maximum depth. Each cycle is divided into 4 steps: loading, holding, unloading, holding. The conditions applied to the test are displayed at the bottom of the monitor. Step 0 begins when we apply a load. This figure is a cross-section of indenter when the load is applied. To evaluate material properties properly, we need to determine precise contact depth, or HC. But our equipment can only measure Hmax, or the depth from reference plane. Therefore, to calibrate contact depth, we look at 2 factors: pile-up and elastic deflection. So as you can see, precise contact depth, HC, is Hmax minus HD plus Hpile. Hmax can be measured by the equipment. HD can be obtained from the Oliver-Farr equation, and Hpile also can be calculated. At step 1, the accepted expression of representative stress is to look to the plastic constraint factor and contact pressure. Tabor verified that the constraint factor is 3 for a metallic material. Representative strain can be defined as a geometrical condition comprised of expressed indenter radius r, contact radius a, and constant parameter alpha. Then, using the load depth curve obtained from step 0, the stress strain points are located. Using the strain stress point, a flow curve is developed at step 2. The element is divided into 2, and the test is carried out optionally. Finally, at step 3, yield strength and tensile strength are obtained using the flow curve. In terms of application, IIT is not limited to any specific material, but can be used for high-strength steel, low-strength steel, stainless steel, and aluminum. More importantly, this flexibility means that IIT can evaluate tensile properties of even unknown materials. IIT's accuracy has been verified by comparing its results with those of existing tensile tests and consistently shows agreement of measurements in various materials. To verify reliability, a round-robin test using IIT was carried out using the same samples from 12 different organizations. The deviation in yield strength and tensile strength was 2.9% and 1.9%, respectively, indicating an extremely insignificant figure. Such RRT result was also applied to ISO TR 29381. IIT can also evaluate residual stress. This step is important because test curve use depends on the existence of residual stress. First, when the test is carried out in a stress-free state, it appears on the graph in a black line. When a compressive stress exists on a test sample, a red line appears during indentation from internal stress. Conversely, a blue line appears when tensile stress exists. With the same indentation depth, the effect of the load varies depending on stress state. A load gap in the stress-free state occurs due to residual stress. Finally, a load gap is applied to the general equation to evaluate the residual stress. For example, as shown in this figure, a stress field is induced by indentation. This hydrostatic stress influences elastic volume deformation in the core during indentation, whereas deviatoric stress influences plastic deformation. In particular, z-directional deviatoric stress is believed to affect the shift of the indentation load depth curve. The residual stress state on the surface of the materials is presented with a tensor form like this, and divided by the hydrostatic stress state and the deviatoric stress state. The graph shows that the degree of load shift is proportional to the z-directional deviatoric stress components. Thus, by quantifying the shift in the indentation load depth curve, residual stress is measured with instrumented indentation tests. Since the z-directional component of the deviatoric stress influences the indentation load directly, deviatoric stress along the z-direction equals the indentation stress. In our example, because the P is about 3 for most of welded material, by inputting this value, we measure the residual stress of SS400 welded specimen. The results show good agreement with conventional methods of measurement, such as hole drilling and saw cutting data. Another result is for the welding of API X80 grade steel. In our work, we applied IIT to equipment to the Advanced Indentation System, or AIS Series. The AIS Series was first introduced in 2000. In its early stage, AIS 1000 and AIS 2000 were developed to evaluate tensile properties, and AIS 3000 was developed in 2005 for evaluating residual stress. Currently, a compact model AIS 3000 Compact and AITU for lab tests was developed. The AIS series allows us to evaluate the tensile properties, residual stress, and failure characteristics of materials in a non-destructive way, and it is portable so that we can use at the site. The test and analysis is user-friendly and can be done automatically. Additionally, a wireless module and battery power enable us to conduct tests at the limited space. The AIS series has been applied to various fields, including pipes and tubes in oil and gas field, pipelines and turbines in plants, and railways and bridges. To illustrate the usefulness of AIS, we have prepared a case showing results from a test involving pipelines performed in Casper, Wyoming, in the United States during August 2007. Evaluation of the tensile properties of the pipe was carried out upon its production and before proceeding with the threading stage. The pipe to test was a freeze tube taken from the sand soil, and its yield strength was evaluated. You can also see the results from testing a natural gas line with GEPII in Mexico in 2002. The material for the test was at 3 to 5 meters under the ground. The lines were mostly 30 years old. Welding joints, which are the most vulnerable parts of a pipeline, were evaluated and their yield and tensile strengths. We also have results from strength measurements of nuclear power plants for identifying the weldment structure at the welding, heat-affected zones, and base positions. We can confirm the deviation of strength on the position like this. We obtain the largest yield strength in weld, as shown the general weldments. This case was performed by SK Energy in Korea. Tensile properties of the 2.25 CR1 Mo were evaluated by treating the overlay welding with SUS 347, and the results were compared with the master block. Considering the unique shape of the test subject, a special jig was fabricated. The support was fabricated with a nozzle penetrating the structure to accommodate the equipment. We found that the 2.5 CR1 Mo appeared to be 5% smaller than the master block at shell base, an indication of stage, not risk. The master block was installed inside after welding during the same conditions, so the nozzle, which is exposed to heat, may be vulnerable to strain. Though there's a difference with the design property, it requires constant monitoring. This is the in-service inspection of the facilities. Using the database from such data, predictions of the material's remaining lifetime were made. This is the in-service inspection of the facilities and the evaluation of degradation on the use period. This is the strength evaluation of CNGV during the manufacturing process stage. This result allowed us to improve strategies used in the manufacturing process. These results identify the variation of strength at each stage of the production process, including the risk stage. This is the case of evaluating the residual stress at major points of finished CNGV. This test identified the cause of defective containers and compared this product to others manufactured both in Korea and abroad. IIT is also useful for testing small samples as well. For example, using IIT, we tested cutting specimens of weldment and fillet samples. As shown in these figures, the size of these specimens is very small, about 2 to 4 centimeters. These sizes are insufficient for using standard methods like the tensile test or the CTOD test. The indentation test was performed along the direction of the arrow. The results show that the strength of welded metal is bigger than that of heated affected zone and base positions of metal. By performing along 3 lines, strength distribution was obtained. In the microregion, we also made a hardness map along the microstructure of API X80. This case evaluated the residual stress of an API X80 pipe when the friction welding method was applied. In addition to IIT, the X-ray diffraction method was applied to compare test results. When analyzing both sets of results, a similar pattern emerged. These similar results indicate that both methods are accurate, but the time taken to use IIT was only 1/10 of the time required X-ray diffraction. In another X-ray diffraction case, we tested a pipeline at a power plant, a chain system. The test was conducted at the heat-affected zone with the base metal. The result of X-ray diffraction is indicated in red, while IIT is in blue. Again, the results are similar, yet IIT was much faster to perform. Here is another example. For analysis of damage caused to a CU pressure vessel, we use the micro-indentation system. Residual stress for silver brazing region was measured and compared with normal and failure specimens. As the results show, maximum residual stress of the normal specimen was 423 MPa, but the failure specimen was 860 MPa. Accordingly, higher residual stress induced in the brazing region caused failure. So, how is IIT being standardized for wider use? Frontics has been continuing the study for establishing the standard while developing the necessary attendant technologies and equipment. The Korean standard was already developed in 2002 and 2005, and ISO TR 29381 was published in 2008. For developing ASTM and ASME codes, Frontics serves as a committee member. Frontics has also produced 2 publications: Metallic Materials, Measurement of Mechanical Properties by an Instrumented Indentation Test, Indentation Tensile Properties, and Measurement of Residual Stress by Instrumented Indentation Test to cover this very subject of IIT application. Looking globally, we are also seeing more cooperation between different countries. The next International Indentation Workshop will take place in Korea in 2011. Many colleges and institutes throughout the world are sharing the technologies for development and advancement together. If you are interested, we hope you will consider attending. In addition, many other companies have been working with us, including JFE Steel in Japan, TWI in UK, and ExxonMobil, Shell, and GE in USA. We will, of course, continue further IIT developments at Frontics in an effort to maximize its practical applications. Thank you for your time and attention.